Momentum is a foundational vector quantity in classical mechanics that measures an object's quantity of motion, defined mathematically as the product of its inertial mass and instantaneous velocity. Because velocity possesses both magnitude and direction, momentum is inherently directional, meaning that proper sign conventions must be rigorously applied along any chosen coordinate axis to avoid critical computational errors. According to the impulse momentum theorem, which derives directly from Newton's second law of motion, the net external force acting on a body over a given time interval produces an impulse that is exactly equal to the object's change in momentum. When analyzing a system containing multiple interacting objects, the total linear momentum remains perfectly conserved over time provided that the system is isolated and closed, meaning no mass enters or leaves and the net external force acting from the surrounding environment is zero. During brief macroscopic events like collisions, internal impact forces heavily dominate over minor external factors, ensuring that total momentum is unconditionally preserved across all categories of crashes. While momentum is always conserved in these closed systems, the behavior of kinetic energy varies dramatically depending on the mechanical and structural properties of the colliding bodies, dividing interactions into three distinct taxonomies. In a perfectly elastic collision, the objects bounce off each other with complete kinetic energy preservation, meaning no energy is dissipated into thermal, acoustic, or permanent structural damage. Conversely, real-world macroscopic crashes are inherently inelastic, meaning that while momentum is conserved, a portion of the system's kinetic energy is irreversibly transformed into heat, sound, or material deformation. The extreme limit of this energy loss occurs during a perfectly inelastic collision, where the colliding objects maximize kinetic energy dissipation by locking or sticking completely together upon impact, subsequently moving as a single unified mass with a shared final velocity vector. This same conservation framework applies in reverse to recoil mechanics and explosive separations, where a static system splits apart due to internal potential energy, forcing the fragmented components to move in opposite directions to maintain a net system momentum of zero.